So yeah, if you missed it for the first talk, there's a recording. And yeah, leaving more time to talk about lattice algorithms.
So yeah, past talk, I talked about algorithms. This talk, I'm going to talk about complexity. Again, another really, really big topic. I'm not going to show you everything. So here's the game plan. I'm first going to reintroduce you to SVP and reintroduce you to CVP really briefly and tell you about the relationship between them. Then hardness, and then we'll end with some nice easy upper bounds. But mostly I interpreted the phrase complexity of lattice problems as meaning hardness of lattice problems. So that's mostly what I'll show you. Okay, so let's just remember that the shortest vector problem is defined as follows. You have a lattice. There exists a shortest non-zero vector in the lattice. Lambda1 is the length of this vector. And SVP is the computational problem that asks us to compute lambda1. So I've sort of cheated here a little bit. In the previous talk, I defined it as a search problem. Now I'm defining it as a decision problem. It's just, in complexity land, it's more convenient to talk about the decision problem. They're not, in fact, equivalent in the approximate version. In the exact, they are. OK. And gamma SVP is the approximate version, so it asks you to approximate this value up to some factor gamma. The closest vector problem is sort of the inhomogeneous variant of the shortest vector problem. So it's the computational problem that asks you to estimate the distance between some target and a lattice. And again, we have an approximate version of the problem given by this approximation factor gamma, larger gamma, easier problem. This is just a very brief list of results for CVP, which are basically the same as SVP. So just like SVP, the exact problem can be solved in 2 to the n time. For polynomial approximations, we can do 2 to the constant n, where the constant depends on the polynomial. And we can get 2 to the n log n over log n in polynomial time. So it's kind of like SVP. And like most of the results we know for SVP, we kind of know for CVP as well. But it seems a lot harder. And like just one thing that I want to mention is the fastest algorithm for CVP is 2 to the n time. And I think that's tight. I don't think that's tight for SVP. Right? We have these heuristic algorithms that do a lot better. For CVP, I think that's actually the right answer. So we think CVP is actually really quite a bit harder than SVP. We don't sort of really know that, though. In particular, there's a formal sense in which CVP is at least as hard as SVP, which is that SVP reduces to CVP. So if you give me a faster algorithm for CVP, it'll also give you a faster algorithm for SVP. And this is due to Oded Goldreich, Daniele Mouly-Safra, and Jean-Pierre Seifert. And it's a really, really elegant, simple reduction. It goes as follows. You consider the following lattice, which I'll call L sub I. And L sub I is the lattice generated by still the same basis, B1 through Bn, except I should have an even coordinate in my ith, on my ith basis vector. So you can either think of it like I doubled the ith basis vector, or like I restricted to the set where the ith coordinate is even. Same thing. And then you just stare at this for a second, and you realize that the distance from Bi to Li, notice that Bi is not in Li, that's kind of important. The distance between Bi and Li is just the minimal length of a lattice vector whose ith coordinate is odd. Yeah? Which means that the lambda1 is just the minimum over all I of these distances. Why? Because a shortest non-zero vector can't have all even coordinates. If all of its coordinates were even, you could divide by 2 and you'd get a shorter vector. So there must be at least one odd coordinate. So one of these minimums has to be lambda1. Does that make sense? Very simple reduction. It's also really powerful, right? Because this reduction preserves both the dimension and the approximation factor. So like really, really, really sort of no matter what regime you care about, whether it's fine-grained or approximate or whatever, CVP appears to be at least as hard as SVP. Good. So that's...
It does call the CVP arc-length time.
Yeah, it does call the CVP arc-length time. I think you can fix that, but I'm not sure.
Using randomization, you can bring it down to a single code, but deterministically it's unclear how to do it.
Okay, so these are very well-studied problems. Here's a small subset of the research that's been done on these problems. So I claim that these problems are interesting from gamma equals 1 to gamma equals exponential, and this is proof. There's been tons of work on this. I'll actually show you a decent fraction of these results in the talk. This is just to scare you. Okay, so another sort of warm-up result. Let's prove that CVP is NP-hard. It's a one-slide proof. It could have been in Karp's original paper, though it wasn't. It's due to Van M. de Boas in 1981, so quite early. The proof just goes, you kind of just remember the definition of subset sum. So remember, subset sum is an NP-hard problem. You're given n numbers and one extra number s, and you look for a subset of the first n numbers that sums to s, right? It's a yes instance if they sum. If there exists such a subset, it's a no instance if they don't. So to reduce this to CVP, there's a very, very simple reduction. You construct the basis B, which in its first, where the vectors in the first coordinates are the A1 through ANs, and on the bottom of the matrix, you just sort of put twice the identity matrix. And then your target is sort of the target value and then the all ones vector, right? And now you just stare at this for a second, and you notice that the distance between the target and the lattice is square root n if and only if there's a solution to the subset sum, right? If there's a solution to the subset sum, then that sort of gives you a 0, 1 vector in this lattice. That's at distance exactly square root n away, right? It'll have some zeros and ones in these coordinates, and it'll have exactly s up here. But any other vector that doesn't satisfy those exact requirements will be distance larger than square root n away. Make sense?
So this reduction is actually from 2001.
Yeah, this is not the original reduction.
I think a 3D matching reduction.
Yes, yes, yes. This is not the original reduction, but I think it's the simplest. Yeah, yeah, yeah.
Find the predicator of Peter? I never found it.
No,
I found it.
Yeah, so it's, there's a scan the PDF
In Dutch.
somewhere online.
Yeah, it's on his website, and you have to go one page at a time. You click like next page, and then you get then it reloads. Yeah, but it exists.
The URL because many people were asking about it. So yeah.
1981. Okay. But this result, I mean, it's beautiful. You know, it could have been proven by Karp, but it leaves some things to be desired. One problem with it is it doesn't give us hardness of approximation, and it doesn't really seem plausible that you could sort of modify it in some simple way to get hardness of approximation. Ideally, we'd like to prove hardness of approximation for polynomial approximation factors. I won't succeed at that today. It also only works for CVP. We'd like to prove hardness of SVP, and it doesn't give us fine-grained hardness. So by fine-grained hardness, I mean I'd like to rule out even a slightly faster algorithm for CVP. I'd like to rule out 2 to the 0.99n time algorithm. Actually, the reduction I already showed you under a plausible complexity theoretic conjecture that I'll mention earlier, it does rule out like a 2 to the n over 100 time algorithm for CVP. So sort of that was already known for quite a long time. But of course, what we really, really want is a very fine-grained hardness of approximation result for SVP. And in fact, based on the results that you'll see tomorrow, these worst case to average case reductions, if we could do this well enough, if we get the approximation factor high enough and the fine-grained enough, this lower bound, sufficiently high, then we would get a statement like this. We would say, no algorithm running in 2 to the 128 time can break this specific crypto scheme. This is way, way beyond the reach of what we know how to prove. I mean, this is, okay, up to the fact that it uses actual constants, this is a much stronger statement than P doesn't equal NP. But
Forget about the fine grain. I mean, this would require sort of polynomial and
no.
it cannot be NP hard, right? For polynomial.
Yeah, unless the polynomial hierarchy collapses. Yeah, but maybe prove a reduction in some other way or something. I'm saying this is the dream result. Yeah, I'll show you reasons why we don't expect to get it, like theoretical reasons, in addition to the fact that we haven't succeeded. But this is how I view this line of work. It's like our goal is to get as close to a statement that would imply this as possible. And that means getting better and better lower bounds for higher and higher approximation factors for the shortest vector problem. That's our goal. And you can, if you sort of don't want a purely theoretical reason for this, you can also just think of this lower bounds on SVP as lower bounds on the algorithms that we actually use to break crypto in practice, which you'll hear a lot more about from Martin. So before I show you hardness of SVP, which is actually really quite difficult, I'll show you a better hardness result for CVP. We're still kind of in easy land. So the way this works, I have to reduce from some problem. So I'll reduce from max 2sat. Remember, max 2sat, it's just a 2CNF, so you're given a bunch of ors of n's, where each or just has 2 elements with n variables and m clauses, and the goal is to figure out how many of these clauses you can satisfy simultaneously. This is known to be NP-hard, to approximate up to a constant factor. I'm saying this like it's no big deal. This is the PCP theorem. It's a very big deal. And the exponential time hypothesis, due to Impagliazzo and Pittori, is sort of one of the foundational sort of fine-grained hardness results. And I'm lying a little bit here, but basically it says there's no 2 to the n over 100 time algorithm for this problem. A more recent conjecture, the gap exponential time hypothesis, due to Dainur and separately by Payson and I'm forgetting the other author, there's no 2 to the n over 100 time algorithm even to approximate this up to some small constant factor, say 1.01. So this is, so when I say I'm going to prove hardness, I mean I'm going to prove hardness under one of these reasonable conjectures, right? Because otherwise, well, we don't know how to prove hardness of anything. Okay. So given that max 2sat is hard, we can try to reduce max 2sat to CVP. Here's how I'm going to do that. So I'm going to construct some basis and some target. And my basis is going to be the first basis you would think of. So the ith row in the jth column, I'm going to put a 1 if xj appears in the ith clause, and a -1 if not xj appears in the ith clause, 0 otherwise. Ti, the target vector, is less obvious. I'm going to put 3 minus twice the number of negated literals in the clause. Not clear why that should work. But suppose you have some 0, 1 vector, and you look at the lattice vector whose coordinates are given by the 0, 1 vector z, and you look at the ith coordinate of that. You stare at this for a second, and you see that it's going to be the number of positive literals satisfied minus the number of negative literals not satisfied by z, if we view z as assignment to the variables. Are you guys with me? Okay. Good. Then if we look at the difference between b times z and t in the ith coordinate, this is going to be twice the number of satisfied literals minus 3. And if you take the absolute value of that, you see that it gives you 1 if 1 or 2 variables are satisfied and 3 otherwise.
Sorry, for those of us a little further from the field, can you remind us what's a literal?
Oh, sorry. Yes, so good. So a literal is like a not x1 or an x3, and a variable is just like the value of x1 or x, or the thing that you set the value to. What other things do I need to? Oh, satisfied means that one of the literals is true. Did I define everything? Okay. More questions? Okay. So the point is that, like, if yeah, so max 2sat is to find an assignment, which here I'm writing as z, so a 0, 1 assignment or a true-false assignment to these variables. The goal is to figure out how many of these clauses can be satisfied simultaneously, or to approximate that. Okay. So if you combine all the coordinates together, you'll see that the squared norm, it's always easier to write the squared norm, is equal to the number of satisfied clauses plus 9 times the number of unsatisfied clauses. So in particular, it's the vector is closer if the assignment is sort of more satisfying. And one thing I cheated here. In CVP instances, we care about all possible coordinate vectors, not just 0, 1 coordinate vectors. But if you stare at this for a second, you'll realize that all other vectors are at least as far away as the 0, 1 vectors. So this is kosher. And what this means is that the distance between the target and the lattice tells us exactly the maximal number of satisfied clauses. This is just another NP hardness reduction. But what's nice about this reduction is, first of all, it maps constant approximation factors to constant approximation factors. So I actually have proven NP hardness here of constant factor approximate CVP for some terrible constant approximation factor like 1.001 or something. And it also maps n variables to n columns in the basis, which is also really nice. This is kind of what I mean when I say fine-grained. In particular, if you remember this gap ETH assumption from before, this means that under the gap ETH assumption, there's no 2 to the n over 100 time algorithm that solves, say, 1.01 CVP, or whatever constant you actually get there. Does that make sense? So like, maybe this doesn't look very impressive, but it's like a lot more impressive than saying there's no polynomial time algorithm, right? We're starting to get a better handle on the actual complexity of the problem. So the state of the art is quite a bit stronger than this. Particularly the best hardness of approximation that we know, which is by Daniele and others. What? Isn't it by Daniele and others?
No.
Oh, I thought you were on that paper. Right. Okay, not by Daniele. Gets n to the 1 over log n approximation factor. So this is known to be NP hard. And this is kind of a funny function, but the way that we think of this, look, log n is a constant amongst friends, so basically this is almost polynomial, right? It's like, and we kind of think of this as like as good as you can do without getting polynomial. Of course, what we'd really like is polynomial, and this is a difficult proof. It uses PCP machinery. I won't show it to you.
It's almost polynomial then?
This is what I'm calling n to the 1 over log n. Yeah, the factor, yes. Oh, you're confusing it with the SVP result. I see.
The reduction is polynomial.
The reduction is polynomial. Yes. It's NP hard, period. The fine-grained hardness that we know, well, under the exponential time hypothesis, we know that there's no 2 to the n over 100 time algorithm for CVP. I actually just showed you that, a full proof. And I also showed you that under the gap exponential time hypothesis, there's no approximation algorithm for CVP. What we actually know is quite a bit stronger, but you need to move to LP norms, which is a little disappointing. So remember the LP norm, so the Euclidean norm is you sum up all the coordinates squared, and then you take the square root. The LP norm is you sum up all the coordinates raised to the pth power, and you take the pth root, and you use some absolute values in there. But we know under the strong exponential time hypothesis, which is a stronger variant of ETH, that there's no 2 to the 0.99n time algorithm for exact CVP, but in LP norms for p not an even integer. And one thing to remember is that 2 is not an even integer. So the norm that we care about is L2. We have this very, very strong result, I think, for LP norms for p not an even integer. So we don't get it for L2, but we come really close. We also know under a very non-standard conjecture, which I'm calling gap SETH, we know that there's no 2 to the 0.99n time algorithm even to approximate CVP up to some constant factor. Again, this is in the LP norms. And one unfortunate thing is that the algorithms don't work in these norms. So we have a 2 to the n upper bound for one norm, and we have a 2 to the n lower bound for other norms. So this leads to my first open question, which is prove hardness of CVP in the Euclidean norm that's as good as we know in the LP norms. And I think this would be a big deal even outside of the Lattice community or the cryptography community, because I think this would be the first fine-grained lower bound that doesn't fall into like a tight fine-grained lower bound that doesn't fall into like a small set of categories. But unfortunately, we've sort of proven that everything we know how to do so far doesn't work. And we even know that the Euclidean norm is provably the easiest norm in the sense that you can embed the Euclidean norm in any other norm. So if you can solve CVP in any norm, then you can basically solve CVP in the Euclidean norm. So there are reasons to think that this is a pretty hard problem, but it'll be a really big result.
The LP result already, I mean, the best algorithm isn't brute force, dynamic programming all meet in the middle.
It's not tight.
Oh, the first, okay.
Yeah. Yeah. There are lots of examples where we know some lower bound and some upper bound. Yeah. Yeah. So that's open problem number 2. Oh no, that's not open problem number 2. Open problem number 2 is very difficult. It's prove hardness of approximating CVP up to a polynomial approximation factor. I'll show you why we don't expect to get too far with this later. There are complexity theoretic barriers, but getting like n to the 1 over 100 or something, we don't know why not to do that. I have an open problem coming later that answers Vinod's question. Okay, so that's hardness of CVP. And I showed you that like actually proving some basic hardness results of CVP is quite easy, right? So it goes back to 1981. So it took us almost 20 years. Van M. de Boas asked in his original paper, is SVP NP hard? And it took us almost 20 years to find the answer. ITI finally answered yes in 1998. Unfortunately, his reduction is randomized. And in fact, all known hardness proofs of SVP are still randomized. So if you care about the distinction between a randomized reduction and a deterministic reduction, then formally SVP is still not known to be NP hard.
Euclidean norm.
This is in the Euclidean norm, yeah. So in the L-infinity norm, things are nicer, and in all LP norms, I think the status is the same. Maybe for P, like asymptotically large or something. And then a very large number of people came around. So Oded and Daniele and Sebastian Cote, and this is a Shai Haviv, came and proved that actually SVP is even hard to approximate. This was a long series of works, some really beautiful results, and I'll show you a little bit of the techniques behind them, or my interpretation at least. So every hardness proof that I know of for SVP, I think of as trying to do the following thing, which doesn't work. So the idea is to use what's known as Canons embedding trick, named after Ravi Canon from 1987. The idea here is, look, I have a matrix and I have a vector. That's my CVP input. My SVP input has to be just a matrix. But like, what's a matrix? It's just a list of vectors, right? So if I want to get just a matrix, I just sort of append T to my list. So I just sort of append T. It's more convenient to take minus T to my my basis. And I add this extra coordinate, and I put some number in there just so that things type check and everything's still linearly independent. So this is like a really, really natural idea. It's kind of the only thing I could imagine doing. And we can look at this and see what it does. So we can look at the lattice generated by this basis B prime, and its vectors look like this. So the first coordinate, it sort of has first n coordinates and a last coordinate. The first n coordinates look like a lattice vector minus k times the target, and the last coordinate is k times s, right? In particular, this means that if you have some lattice vector, if you have some vector in the original lattice, then you have the vector y minus t comma s in the new lattice, which means that essentially lambda 1 of the new lattice is at most the distance. You lose this little factor s. But if you have a close vector in your original lattice, then your new lattice will have a short vector, right? But there's a problem with this, right? Does someone see the problem? The problem is that there are other short vectors as well, right? Not all vectors in this lattice take this form. More in particular, you can have k not equal to plus minus 1. K minus 1 is sort of the same thing. You just get minus the closest vector instead of plus the closest vector. And actually, it turns out, sort of because you can tune this s and for some other more technical reasons, that the only actual problem is the k equals 0 issue. So k equals 0 corresponds to short vectors in your original lattice. So clearly, if your original lattice has short vectors in it, then this reduction won't work, right? Because my new lattice will still have those short vectors, and I'll compute lambda 1, and it'll just tell me your lattice has short vectors in it, which I already knew, right? So not useful. So the ideal solution to this would be to say, just assume that there are no short vectors. And this is not a bad idea. If you assume that there are no short vectors that are shorter than the distance, then you've assumed that you have a bounded distance decoding problem up to constant factors. And bounded distance decoding is a very important problem, but we need to prove hardness of bounded distance decoding in order to make that useful. So the real solution is we make a much weaker assumption. We assume that there aren't too many short vectors in our original lattice. And it turns out that that's enough. Got out of order. So in order to talk about this a little bit more, I'll have to introduce some notation. So I'm going to write n of LR for the number of vectors of length at most r in a lattice, and I'll write n of LRT for the number of vectors at distance at most r from some target t. Okay? So number of short vectors, number of close vectors. And what we would like is the number of short vectors to be much, much less than the number of close vectors. And I'll show you why in the next slide. So heuristically, there's just many more close vectors than short vectors. And the reason why is because we can use a trick due to Sebash-Coate known as sparsification, which works as follows. It's closely related to like these I-tie lattices, these Q-area lattices that Daniele talked about. So we can define the lattice L hat to be the set of lattice vectors, so still B prime times Z, so still things in the lattice generated by B prime, but we make a restriction on the coordinates. We say that the coordinates have to satisfy some linear equation mod Q. So inner product of Z with some vector A has to be 0 mod Q. What is A? We'll choose A randomly from the appropriate set. That should be ZQ. I guess you can take it from C. So if we choose A randomly, then the vectors in this L hat, they look essentially like we just randomly and independently looked at each vector in our original lattice and kept it with probability 1 over Q and otherwise threw it away. This is obviously a lie for a lot of reasons. In particular, this is a lattice, and if I did that process, I wouldn't get a lattice. But morally, this is what's going on, and you can prove, for example, here you don't have pure independence, but you do have pairwise independence, which is already enough. So we have this procedure that sparsifies our lattice. It takes our lattice and it sort of randomly samples a Q fraction, a 1 over Q fraction of the lattice points. So if we take our value Q to be roughly the number of close lattice vectors, then when we do this operation, we'll be left with roughly 1 close lattice vector remaining. And if we had many, many more close lattice vectors than short lattice vectors, then all the short lattice vectors will be gone. So this is the sparsification trick, right? So if the initial CVP instance had a bunch of close vectors and not too many short vectors, then the final CVP instance will have no short vectors, just close vectors, right? And then we'll actually be able to, then the reduction will work. The original reduction will work. So it turns out that if you want to show hardness of SVP, if you sort of unwind this, it suffices to show hardness of CVP with many more close vectors than short vectors, right? If you can show that an instance of CVP that has this funny property is hard, then you'll prove hardness of SVP. So we need some way to increase the ratio of close vectors to short vectors. And to do that, we use a gadget. I like to write my gadgets with daggers, so my gadget will be B dagger and T dagger, a basis and a target. And I'm going to use my gadget in a sort of simple way. I'm going to define L tilde to just be the lattice generated by this matrix, B0, 0, B dagger. And I'm going to define T tilde to be T dagger put under T. And of course, this is the direct sum of the two lattices, a direct product if you prefer, right? So lattice vectors in L tilde just look like pairs of vectors, the first in LB and the second in my gadget lattice. And this equation is slightly complicated, but the idea is that the number of short vectors in L tilde should look roughly like the product of the number of short vectors in my original lattice and the number of short vectors in my gadget lattice. So I'm hand waving aggressively here, but the rough idea, if you have a short vector, because I'm not defining short, but if you have a short vector in L tilde, then it must come from a pair of vectors, one that's short in the original and one that's short in the gadget, right? And ditto for close vectors. The number of close vectors is going to be something like the product of the number of close vectors in the lattice with the number of close vectors in the gadget. So if we want the resulting lattice to have many more close vectors than short vectors, what we need is for this ratio, the number of close vectors in the gadget to the number of short vectors in the gadget, to be much, much larger than the number of sort of annoying short vectors in our original lattice. And the number of short vectors in our original lattice, well, we don't really know what it is, but it can't be greater than 2 to the poly n, because if they're short vectors, we should be able to write them down. And if we can write them down, then they're at most 2 to the poly n of them. Does that everything check? Okay, suspicious. Yeah.
It's backing bounds. You can come up with
Yeah, this is true. You can bound the number of short vectors. Yeah. I'm just being lazy. Good. And Daniele, I think, coined the term locally dense lattice for these lattices. So the idea here is that these lattices have this surprising property that there's some ball in which there are many, many lattice points. In fact, significantly more lattice points than there are in the centered ball of the same radius. So they're lattices that happen to have some strange dense region somewhere. And I believe all hardness reductions for SVP use a gadget that satisfies this property. Most of them use additional properties for various reasons. But we did show recently, it was probably already known to folklore, that in fact, any such gadget already implies if you have such a lattice, then you get hardness of SVP. So these are hard to build. I'm not going to show you how to build them. I'll just sort of tell you what we've done and what we get out of it. Yeah.
You understood 2 to the poly as a lower bound?
I think it was an upper bound.
Poly, I'm not sure. Upper bound. Oops. Oh, you want less. Yes. You wanted over the ratio, over the ratio.
Oh, yeah, so it has to be larger than this, which is at most 2 to the poly. Yeah, asymptotic notation can do funny things. Okay. So we want this ratio to be larger than 2 to some polynomial in the dimension of our gadget lattice, which I'll write as n dagger. And actually, formally, we need very slightly more than that, or maybe not so very slightly. We actually need to be able to throw some approximation factor gamma down here. So we actually need our definition of short to be a little more forgiving than our definition of close. And there's tons of work on constructing these things. The current state of the art, and the reason we care about these things, the larger gamma you get, the better hardness or approximation result you'll get, which maybe is intuitively kind of appealing. And if you get this polynomial, so normally you might expect this polynomial to be n to the 1/3 or something small, but if you can get this polynomial all the way up to linear, which is provably optimal, then you can get a fine-grained hardness result for SVP. You can prove that there's no 2 to the epsilon n time algorithm for SVP under gap ETH, which I showed you earlier. And it turns out that there do, in fact, exist L dagger that kind of satisfy both these things simultaneously. So they have an approximation factor, or they have this gamma factor that's larger than some constant, and they have they have exponentially many more close vectors than short vectors. We showed this recently, joint work with Devesh. And in particular, this implies that there's no 2 to the epsilon n time algorithm for 1.0001 SVP under gap ETH. So this is a sort of hard-fought result. And I think the moral interpretation is that we're not completely out of the ballpark on our SVP algorithms, right? This tells us that we don't expect to find a 2 to the square root n time algorithm or something that just totally different than everything else we've already done. Ideally, what we'd like to show is that this 4/3 to the n over 2 or 3/2 to the n over 2 or something is the right answer. But this is what we actually know how to prove. Interestingly, the way that we do this goes through, so we were only able to do this recently because we used a result that was proven very recently by Vladut. So Vladut showed a lattice with exponentially many vectors that all had minimal length. So Vladut showed that there are lattices with large kissing number. And you might remember from my previous talk that the kissing number featured prominently in the study of sieving algorithms. And I think that this relationship is really extremely interesting. The fact that our best lower bounds and our best upper bounds both go through the kissing number kind of suggests that maybe we're doing something right. Because obviously our goal is to make the upper bounds match the lower bounds. And if they both use the same stuff, then that's good. So
Only randomness here that comes from sparsification, is that right?
yeah, that's a lot of randomness, no?
What about finding dense? You don't need that.
Okay, for the L2 norm, we do. In fact, the L2 norm is non-uniform because I don't know anything about this lattice. But for other norms, for p larger than 2.14, we don't. Because our gadget is the integer lattice. Okay, so for the Euclidean norm, the best result that we know is what I just showed you. There's no 2 to the epsilon n time algorithm for constant factor approximate SVP for some terrible constant approximation factor. For LP norms, just like for CVP, for SVP, we know a lot more. We know very strong hardness results. We know that there's no 2 to the C times N time algorithm for SVP, where C depends on the norm in this way. It's not clear at all if this is sort of the right answer because SVP in these norms is very poorly studied. But I guess the point is that we can prove very strong hardness results, just not in the right norm. And this is based on joint work with Devesh and Huck, who are both here, even sitting next to each other, and with Sasha Golovnev. And the open problem that's obvious is to get better fine-grained hardness results for the Euclidean norm. So this is like one of the holy grails, I think. And I'll even ask a really, really bold question, which is, can we get matching upper and lower bounds under just a conjecture, a geometric conjecture? Again, I'm kind of excited about the fact that somehow the kissing number appears multiple times. So I think this might plausibly be maybe kind of sort of doable, which is exciting. Yeah.
Help me interpret the original proof of ITI in this framework, because the construction of the lattice that he uses seems very different from what you're discussing.
Yeah. I don't know. Daniele probably knows better than me.
There was not using sparsification, but I still had the locally dense.
It did, yeah.
So the locally dense part, it was not described there explicitly,
But it is buried somewhere in there.
Has the locally dense gadget used explicitly.
So he constructed a locally dense gadget out of those
Prime numbers. Yeah, those prime numbers can be turned into a locally dense lattice, and then you use that. So if you do that, and also in Lattice proof, the reduction was randomized with one-sided error. The sparsification is introducing randomization and error on the other side, so it becomes a two-sided error. But the subsequent work is going back to one-sided error, and essentially, yeah, the center of the locally dense lattice, that's the main issue for some randomized proofs.
Right. Right. Yeah. If we can find these gadgets deterministically, then we'd have Daniele prove this. Then maybe need a couple more properties of the locally dense lattice, just locally dense.
Center.
Yeah. Then we'd have deterministic. Okay. But yeah, I really think this is plausible, which I'm excited about. Open problem number 4, which I thought I put earlier. I'm going to fix that immediately, because that seems bad.
Do you have the...
Yeah, I do.
I just didn't think I read it.
Okay, so open problem number 4 is to find algorithms for SVP and CVP in the LP norms. So Daniele mentioned this earlier. I think this is an interesting question just on its own. As I said, Devesh has a result in this area together with Priyanka Mukherjee for the L infinity norm, but this is really like largely unexplored territory. And it's interesting in its own right, and I also think it's just interesting because of these lower bounds. Like matching upper and lower bounds are rare things, and here we have no idea if we have them because we haven't really thought about the problem that much. And number 5, I think these locally dense lattices are really very beautiful objects on their own. I think they're worthy of study independent of hardness of STP. In particular, we can imagine proving upper and lower bounds on these things. And like for some norms, like our constructions are very natural. It's plausible they might be optimal. So I think these are interesting, fun things to study if you're into that kind of thing. So now I'm going to say a little bit about hardness or approximation. Unfortunately, the way these proofs go, you can sort of either say a little or a lot, I think, so I'm going to say a little. So we proved hardness for constant factor approximation, for bad constant factor approximation. The idea, which was originally due to Sebash and then was improved by Shai and Oded, is to boost the approximation factor. Imagine this idea was actually around before that. The idea is to take the tensor product of the lattice with itself. So this means like you sort of replace your basis matrix, but well, you do replace your basis matrix by the tensor product of the basis matrix with itself. So like every entry in the new basis matrix is the product of 2 entries in the original basis matrix. One issue with this is that it blows up the dimension. So you start out with an n by n matrix, you end up with an n squared by n squared matrix, just doing this once. But the good thing is that it maps the shortest vector to the length of the shortest vector to the length of the shortest vector squared, which means that your approximation factor gets squared. I hear squirming in the audience. This statement here is the intuition for why this should work. It's not entirely true. If this were true, then I would be done proving hardness of approximation for larger approximation factors. But this is actually very false in general. So the whole game here, which is a difficult game, is to find lattices or find variants of tensoring that make this fact true. But I'm sort of just not going to go into that at all because it's its own world.
Go into that. Is it just tensoring and then sparsification?
I don't think that works.
Okay.
To do what?
To get this sort of.
No, that's not true. I mean, it is true if the lattice is in dimension less than 42, then it is true. But then you're not going to find explicitly an example where that's not satisfied. That doesn't get squared.
No, they're explicit examples. Self-dual lattices satisfy that. Self-dual lattices with the lambda 1 equals square root n. It doesn't get squared, yeah. Yeah, in fact, it's much worse than squared. It's like squared divided by root n or something.
Typical lattices, it does get squared. That's what you're saying?
Yeah.
And if you take an arbitrary lattice, tensor it, and then sparsify it, you're somehow taking a sublattice of a random sublattice of a...
Yeah, that's a nice idea.
You want to prove things.
True, but I thought that's how the plugin works.
It's plausible that you could reinterpret it that way. I mean, that's not what they looked at very specific properties of the lattice. Yeah, maybe looking back on that paper.
I guess I'm missing a homogeneity constraint here. Are we talking about integer lattice or volume 1 lattices? Or?
I don't think it matters. So I'm just saying that the lambda 1 squares, whatever it is, that makes sense, right? I mean, it's not true, but it makes sense. And then the approximation factor would square, right?
It is true for linear codes in the Hamming magic, for example.
Yeah.
In that case, it's always true.
Right.
In Euclidean norm, yeah, that's messy.
Yeah. Okay. So using these ideas, you can get NP hardness for any constant approximation factor. That was originally proven by Sebash. And that's like modulo the fact that this lambda 1 thing isn't true, that's kind of immediate from this, right? Because I can tensor as many times as I want. I'll go from dimension n to n squared, and then I do it again, I'll get n to the 4, and then n to the 8, etc. But I can do this a constant number of times, I'll still be polynomial. So that's okay, and we can get as large a constant as we want. Haviv and Regev showed a sort of orthogonal result. They showed that there's no polynomial time algorithm for n to the 1 over log n SVP, but not under polynomial time reduction. The running time of the reduction is much larger. So they only show that there's no polynomial time algorithm if there are no sub-exponential time algorithms for NP, if that makes sense. And this just comes from this tensoring thing. You have to tensor a super constant number of times so you don't get a polynomial time reduction. But you'll notice this is the same approximation factor that we have for SVP. It's just a weaker hardness result. So a natural open question, which if a node thinks is within reach, is to prove just straight NP hardness for n to the 1 over log n SVP. So in other words, just extend what we already know for CVP to SVP. I don't know, maybe Vinod has more thoughts on how this would go. Maybe it would adapt PCP machinery or something. But yeah, Vinod thinks this is within reach. And maybe you can coax him. He's been known to give $100 to people who solve problems. So maybe you can coax him. Oh.
I've been made poorer many times.
We can have an auction later. Okay. The other question is to prove better fine-grained hardness approximation. In particular, this tensoring thing is very much not fine-grained in the sense that just doing it one time takes our dimension from n to n squared. So you can think of that as taking hardness from like 2 to the order n to like 2 to the order square root n, which like we're already really not happy with. We'd like to prove exponential hardness of these problems. So I think a really interesting question is whether we can boost the approximation factor without squaring the dimension. Maybe even not even in a polynomial time reduction. You can use 2 to the n over 100 time, I'd still be happy. And I think any new idea here would be interesting. Anything that's not tensoring would be really interesting, even if it doesn't give new results. Because this is sort of the, as I see it, kind of the new frontier. In particular, this is how we get closer to this unachievable goal of proving that crypto schemes are actually 2 to the 128-bit hard. We have to get higher and higher approximation factors. Or right now, we just don't know how to go higher than like 1.01. Okay, so now I'm going to show a couple upper bounds, which from this perspective are really lower bounds for lower bounds. In particular, I'll show you why we don't expect to prove NP hardness for arbitrarily large polynomial approximation factors, say. What I mean by upper bounds here, I gave a whole talk on algorithms. And usually when you say upper bounds, you mean algorithms. I think what I mean here is I'm going to place these problems in complexity classes. So I'm going to use non-standard definitions of algorithms, essentially. And the first main result, I think, in this area is due to Shafi and Oded. Shafi here. Back in 1998, they showed that an all-powerful prover, say Shafi, can convince a bounded verifier like myself that the distance between the target and the lattice lies in some range, where the gap in this range is a factor of root log n over n. So that's kind of the approximation factor. And notice that, so one step in this proof is easy. Remember, Shafi, as you know, is all-powerful. So if she wants to prove to me that the distance between the target and the lattice is at most r, she just exhibits a close vector, right? This is easy. This is saying CVPs in NP would be the language here. The difficult part is going in the other direction, right? So like, stop and think about it for a second. Like, how would you show someone that there's not a close vector in a lattice, right? It's kind of like saying that a formula is not satisfiable or something. Even though Shafi's all powerful, it's not clear that she can convince little old me that such statements were true. And what this means, why I call this a lower bound for lower bounds, is it means that we don't expect to prove MP hardness for root n over log n CVP, or also root n over log n SVP, because if we did, then the polynomial hierarchy could collapse, which basically means like complexity theorists would be very upset with you. So we don't expect to do this. People didn't like that joke. Okay, so let me show you the protocol. It's really quite beautiful and quite simple. The idea is, so you start out with a CVP instance, right? So we have a lattice and we have a target. I've drawn my target sort of far away from the lattice because the difficult thing for Shafi to prove is going to be that we are in fact far away from the lattice. So how are we going to do this? Well, first I'm going to consider not just the target point itself, but all shifts of the target point by lattice vectors. So these are shifts of the target point by lattice vectors. And I'm going to imagine a ball of radius r over 2 around every such point. And here's what I'll do. I'll pick one of these points randomly. You have to be careful about what you mean by picking randomly from a countably infinite set, but you can make this precise. I'll pick one of these points randomly, say this one. So I pick this ball, and then I just sample a uniformly random vector t prime in this ball. It's not clear why I'm doing this yet. It's just because I like doing such things, but it'll work. And so that's one sort of thing that I can do. Another thing that I can do is I can pick a uniformly random vector in a ball around a lattice point. So these are sort of the two different games I can play. I can either pick a uniformly random ball around a shift of t, or I can pick from a uniformly random ball around a shift of a lattice point. So now what I will do is I'll tell Shafi, hey, here's my point. And Shafi will tell me whether it came from the blue set or the red set, whether it came from, whether it's close to the target or it's close to the lattice. That's all Shafi does. And notice that if the distance is in fact larger than r, then Shafi can always distinguish between the blue set and the red set. They're disjoint, right? So she always knows whether I chose blue or red. That's just, I guess, triangle inequality. On the other hand, if t happens to be very close to the lattice, and if you don't know much about high-dimensional geometry, where this root log n over n factor comes in will not be clear. But if t happens to be close to the lattice, then these two sets have to overlap quite considerably. And this root n over log n is just sort of how this works out in high dimensions. So no matter what Shafi does, if I pick this point here, she's not going to be able to tell me whether it came from the blue set or the red set because it's equally likely. Right? So this is a sort of funny notion of proof where the way Shafi proved something to me is she just proved that she could do something. She didn't argue about it. Good. So actually, this is a statistical zero knowledge proof, in case you know what that means. This is a little stronger than what I showed you. But the moral of the story is for approximation factors above square root n over log n, we don't expect to prove MP hardness. So there's a similar upper bound. The result's similar, the proof's not. Oh, I didn't fix the approximation factor here. But Dorit and Oded showed that square root n CVP is in co-NP. So I just showed you co-AM. And the reason that was a co-AM protocol, I didn't even define co-AM, but co-AM involves me talking to Shafi and Shafi responding. A co-MP protocol is Shafi doesn't have time to talk, so she just sends me an email, right? And so Dorit and Oded showed how to prove that this distance is at most r and at most r over square root n, that log n shouldn't be there, in a non-interactive way. Non-interactive, no randomness. And the moral of this story is that if we proved MP hardness of square root n CVP or square root n SVP, the polynomial hierarchy would still collapse, but it would be like even worse. So we like very much don't expect to prove this. It's also just a beautiful result, so I want to mention it. There's actually a new line of work by Katerina and Manolis and Georgios, who's not here, and that's not a picture of him. He doesn't have a picture online. If you Google him, this is what you get. Daniel Wicks, his advisor. But they proved that for an n approximation factor, SVP is in PPP, which means we really don't expect to prove NP hardness of n SVP because otherwise Christos Papadimitriou would be unhappy. Okay. So in summary, we know quite a bit. I think I've shown you, or at least mentioned, sort of everything on the left side of this. And you'll be hearing about the crypto applications of SVP in future talks. So a lot of the results that I've shown on this crazy, scary slide will actually be part of this workshop. But I guess like the 30,000-foot summary is that we know hardness for almost polynomial factors. We know fine-grained hardness for like near exact, like small constant factor approximations, and we don't expect hardness for root n over log n. So you might guess what the open problem would be. One obvious open problem is to do something between this upper bound and this lower bound. Been this way for quite a long time. And so we know nothing that suggests that we can't prove n to the 1 over 100 hardness. And we also know nothing that rules out the possibility that maybe for like n to the 1/4 or something, CVP lies in your favorite complexity class. So I think this is...
So want to mention something. So if you assume something, a crazy conjecture related to the label cover problem,
Yeah.
it's consistent with the algorithms for it.
Yeah.
Then I think you can show actually like you
It's
can show
about 6 or something? Yeah. 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 Yeah, so there is, I don't understand this result, so which is why I didn't talk about it.
Maybe you're saying you don't understand the conjecture.
Yeah, that's what I mean. Yeah, so there is in fact a result in this area that I did not include, which is an n to the 1/6 hardness under a non-standard conjecture. But I still think this is open, and I think in particular upper bounds, the polynomial hierarchy doesn't end at co-NP or co-AM. It goes for a while. So one can maybe plausibly expect to find additional upper bounds to explain why we seem to be stuck. Although maybe we're not stuck.
So you think we may get as close as to n to the 1/2 minus epsilon, constants less than 1/2? Or,
Yeah, I mean, actually, there are some things that you can do, I guess, upcoming work with many others. There are some things that you can do in this regime, but like, what do I want to say? I mean, I don't know. Has anyone thought about going 7 levels up in the polynomial hierarchy or something? Like, I think it's plausible that this sort of wilderness is not can be explored more. Okay, so I'm almost done. Let me just list open problems for you, conveniently labeled with skiing notation. Right, so they actually ended up being sorted, it's not intentional. But we have some hard problems, which are to prove better hardness results, I guess. In particular, to get tight fine-grained hardness for exact CVP in the Euclidean norm, tight fine-grained hardness for exact SVP in the Euclidean norm, and hardness for polynomial approximation factors. So all of these are open and seem quite difficult. Potentially easy open problem. Of course, these are just my guesses. I don't know how hard these problems will be because I haven't solved them. But a potentially easy problem is to think about better algorithms in the LP norm. I think that's not very explored. So I recommend people try. And then a bunch of medium problems. There's this geometric question about a better understanding of locally dense lattices. There's Vinod's question of proving NP hardness of n to the 1 over log n SVP. So matching what we know for CVP. There's fine-grained hardness approximation. which I think might be not too hard for CVP, but probably very hard for SVP, but what do I know? And there's coming up with an upper bound somewhere in the regime, the no man's land, where we don't know much. And I think that's it. That's it. Yes, I'm on the job market.
Steve.
Yeah.
Any more questions? Yes, sir.
Yeah. So you mentioned a lot about the kissing number.
Yeah.
So you defined it as something with the number of spheres you can have on a sphere and some dimensions.
Yeah. So it's the number of points you can put on a sphere, such that say a unit sphere, such that all points are at least distance 1 away from all other points.
Then you mentioned the kissing number of a lattice.
Yeah. So that's the same thing, except the points should be shortest points in a lattice. Yeah, they have to belong to a lattice. So yeah, it's the number of shortest points is the easier way to say it. Yeah, and they're not known to be the same number.
But we do know about lattice with exponential.
Yeah, yeah. So Vladuc very recently proved in 2018 is a major breakthrough that there are lattices with exponential kissing number. Yeah, like 2 to the n over 50 or something like this.
What kind of construction?
Algebraic geometric codes. You've exhausted my knowledge of the.
So I have a question about this diagram. I guess it's from a couple of years ago.
The crazy one? Okay, yeah.
One of your notes, right? Are there any updates on this diagram?
Well, I made one update in 2016. That was the introduction. There are things that aren't included, but I think the short answer is not really, not much. Daniele can tell me if I'm wrong. This is
It's hard to look at them.
well, the question is, have there been like significant advances and reductions between worst case lattice problems in the past 4 years?
Yeah.
Yeah. Yeah. I mean, you can see that this is Daniele's diagram. Really. There are a lot of M's.
Thank you.